Alright, this is the third video on section 6.2 and we're looking at properties of power series. Problem number 7 says to evaluate the sum n equals 0 to infinity of negative 1 to n divided by 2n plus 1. And we're provided with a hint that says write it as the integral from 0 to 1 of f of t dt, where f of x is equal to the sum n equals 0 to infinity of negative 1 to the n x raised to the 2n, and that is equal to 1 over 1 plus x squared. So we're going to go ahead and find the integral from 0 to 1 of f of t dt, which is going to be equal to the integral from 0 to 1 of the sum of n equals 0 to infinity and then negative 1 to the n, and then instead of x we'll use x to the 2n dt. And so we're going to look at term by term integration. So the integral from 0 to 1 of 1 minus t squared plus t to the 4th minus t to the 6th plus all the way out to the nth term, which would be negative 1 to the n t to the 2n, etc. dt. So performing the term by term integration, that's going to be t minus t cubed over 3 plus t to the 5th over 5 minus t to the 7th over 7 plus dot dot dot. The nth term would be negative 1 to the n t to the 2n plus 1 divided by 2n plus 1, etc. And then we're going to evaluate that from 0 to 1. Not from 0. Yeah, we're going to evaluate that from 0 to 1. So that's going to give us 1 minus 1/3 plus 1/5 minus 1/7 plus dot dot dot. Negative 1 to the n. 1 to the 2n plus 1 is just 1 all over 2n plus 1 plus dot dot dot. If we write this as a series, this is going to be the sum n equals 0 to infinity of negative 1 to the n over 2n plus 1. And usually you use that nth term to kind of get your term in your series here. Okay, so that's just the antiderivative here. And so we took the antiderivative of the sum n equals 0 to infinity of negative 1 to the n x to the 2n, which is equal to 1 over 1 plus x squared. And so that'll have the same antiderivative. So if we do the integral here from 0 to 1 of 1 over 1 plus x squared, in this case we're going to use t squared dt, that's going to be equal to the arctangent of t evaluated from 0 to 1. And so here's your arctangent right here. Okay, it's that antiderivative. Okay, and we're going to evaluate that from 0 to 1. So that's going to be the arctangent of 1 minus the arctangent of 0. The arctangent of 1 is going to be pi over 4, and the arctangent of 0 is going to be 0, and so the value of this sum is going to be pi over 4. Alright, we got 3 more to go, so let's look at another example here. Example number 8. And we're going to find the power series for f of x is equal to the natural log of 1 minus x to the 8th, and this is going to be centered at x equals 0. And we're going to use either term by term integration or differentiation. What we're going to do is we're going to look at the derivative of the natural log of 1 minus x to the 8th. So that derivative, okay, so the derivative natural log of u is going to be u prime over u. So u prime would be negative x to the 7th power, and then u would be 1 minus x to the 8th, so that's just taking the derivative. And this is a geometric series here. Sum n equals 0 to infinity. A would be 8x to the 7th, and your r would be x to the 8th, and then we'll raise that to the nth power. And so this will be convergent provided that the x is between negative 1 and 1. Let's go ahead and simplify this down a little bit further. This is going to be the sum n equals 0 to infinity of negative 8x to the 8n plus 7. Okay, And so what we're going to do is we're going to look at what this is term by term. So negative 8 times x to the 7th plus x to the 15th plus dot 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 x to the 8n plus 7, and etc. So we took the derivative of the natural log of 1 minus x to the 8th, and we got this power series. Now to get back to the natural log, we're going to have to do the antiderivative, so now we're going to do the antiderivative of this. So the natural log of 1 minus x to the 8th is going to be equal to the antiderivative. We'll go ahead and do the definite integral of 0 to x of the sum n equals 0 to infinity of negative 8 t to the 8n plus 7, so we're going to use a different variable t here. So it's going to be the integral from 0 to x of negative 8 times t to the 7th plus t to the 15th plus dot 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 t to the 8n plus 7, and keep going, and we're going to integrate with respect to t. So just a bunch of power rule. So negative 8's out in front, and t to the 8th over 8th plus t to the 16th over 16 plus dot 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 t to the 8n plus 8 all over 8n plus 8 plus dot dot dot, and we're going to integrate this from 0 to x, so we're essentially going to replace all the t's with x. So negative x to the 8th plus x to the 16th over 2, so I went ahead and distributed the minus 8 through, plus dot 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 x to the 8n plus 8 all over n plus 1, and etc. So our series for the natural log of 1 minus x to the 8th is going to be negative sum n equals 0 to infinity of x to the 8n plus 8 over n plus 1, and that's provided that the x is between negative 1 and 1, and we have our convergence. Okay. All right, we're going to look at a very similar function, and we'll look at a slightly different approach of finding the power series for it. So number 9, we're going to look at the function f of x is equal to the natural log of 1 minus x squared, which, using properties of logarithms, we can split this up. So first we'll factor it. The 1 minus x squared is 1 minus x, 1 plus x, difference of squares. And that's going to become the natural log of 1 minus x plus the natural log of 1 plus x. And then if we take the derivatives of these, we'll make it look like geometric series, and we'll use our geometric series formula to convert them into power series. Alright, so we're going to take the derivative of the natural log of 1 minus x squared, which is going to be the derivative of the natural log of 1 minus x plus the natural log of 1 plus x. Those would be negative 1 over 1 minus x plus 1 over 1 plus x. And then we need to write them as a over 1 minus r, so we can use the geometric series formula. So the first one's good to go, negative 1 over 1 minus x, plus the second one we'll write it as 1 over 1 minus negative x. And so that's going to give us the sum n equals 0 to infinity of negative x to the n, plus the sum n equals 0 to infinity of negative x quantity to the n. Okay, and what we're going to do is we're going to write out some terms of each series here, and then we'll add up the coefficients on the like powers. So the first one we'll have is negative 1 minus x squared minus x cubed minus x to the 4th, etc. minus x to the n, etc. Plus the second series will be 1 minus x plus x squared minus x cubed plus x to the 4th, all the way out, and we have alternation there. So it's going to be negative 1 to the n, x to the n, etc. And so we can start combining our like terms. So the negative 1 and the 1 will cancel, but we have a minus x and a minus x, so a minus 2x. The negative x squared and the positive x squared will absorb, so I have a minus 2x cubed minus 2x to the 5th. And so what's going to be remaining here is the odd powers of x. We're going to have negative 2 of them, all the way out to negative 2x to the 2n plus 1. So the 2n plus 1 is just a way of representing a generic odd power somewhere out there, etc. And we'll write this as the sum n equals 0 to infinity of negative 2x to the 2n plus 1. So that's what the natural log of 1 minus x squared's derivative is. So to find the power series for natural log of 1 minus x squared, we need to find the antiderivative. So we're going to do the integral from, and we could do the integral from 0 to x if we wanted to. Here we're just going to do just the antiderivative. So the integral from integral of, and how do we say this? The integral of the sum from n equals 0 to infinity of negative 2 x to the 2n plus 1, integrate with respect to x. So when we integrate that, we're going to get a constant of integration, and we're going to integrate the negative 2. Let's see, the negative 2 will slide it out, and the x to the 2n plus 1 will add 1 to that exponent, so it'll be x to the 2n plus 2, and then we'll divide by the exponent of 2n plus 2. Okay. Then to solve for the constant of integration, let's pick a value for x. So if x is equal to 0, by the way, both of these, in order for us to have these convergent power series, the x needs to be between negative 1 and 1. If x is equal to 0, then we have the natural log of 1, which is 0, and then c minus 2 times the sum n equals 0 to infinity of 0 to the 2n plus 2 over 2n plus 2. So that's all going to be 0, all of this right here. So we're going to have the natural log of 1 is equal to c, but the natural log of 1 is 0. And so this is going to tell us that c is equal to 0. And therefore, the natural log of 1 minus x squared is equal to negative sum n equals 0 to infinity of x to the 2n plus 1 over n plus 1. And I went ahead and did one more thing. I saw the factor of 2 and then the divisor of 2, so we can go ahead and reduce there. Okay? Alrighty, so last example, one more. We're almost there. Okay, so we'll mention the interval convergence there. Okay, and last example here, we're going to express this series, the sum n equals 1 to infinity of 1 plus x to the 8th, and then that 1 plus x to the 8th quantity to the negative n, in terms of elementary functions. So think of polynomials, rational functions, sine, cosines, trigonometric, typically any function that we've dealt with, other than if it's got a power series representation, or can only be represented as a power series. Anyways, so we're going to express this as an elementary functions. The sum n equals 1 to infinity of 1 over 1 plus x to the 8th and then raised to the nth power. Well, that's just a geometric series. 1 over 1 plus x to the 8th plus 1 over 1 plus x to the 8th squared plus 1 over 1 plus x to the 8th cubed, etc. So the problem is with a geometric series, it starts at 0. You know, you have the sum n equals 0 to infinity of a r to the n. So we start at 0. And so we're going to have to make an adjustment to use our geometric series formula. So what we're going to do is we're going to add and subtract 1. So we have a negative 1 plus 1. That doesn't change anything. And then the rest of the series. 1 over 1 plus x to the 8th plus 1 over 1 plus x to the 8th squared plus 1 over 1 plus x to the 8th cubed, and etc. Alright, so that negative 1 we're just going to leave there. The 1 here, we can write that as 1 over 1 plus x to the 8th to the 0, and we can put that in with our series now. It's going to be negative 1 plus the sum n equals 0 to infinity of 1 over 1 plus x to the 8th raised to the n power. Now we can use our geometric series formula. So we have the negative 1 plus, and it's going to be 1 over 1 minus the common ratio. Common ratio is 1 over 1 plus x to the 8th. It's going to be equal to negative 1 plus 1 plus x to the 8th. So we're going to multiply the numerator and denominator by 1 plus x to the 8th over 1 plus x to the 8th minus 1. Okay, and then I'm going to multiply the negative 1 by 1 plus x to the 8th. So it gives us negative x to the 8th plus 1. Oh, no. Sorry, guys. I'm going to multiply the negative 1 by, let's see, the denominator here is x to the 8th. That's what I did. Okay, sorry about that. Okay, so negative 1, we're going to multiply by x to the 8th over x to the 8th, so we get a negative x to the 8th in the numerator, and then we have a 1 plus x to the 8th here, and then all over x to the 8th. So that simplifies down to 1 over x to the 8th there. And so that would be our elementary function here, which is a rational function. Okay, so that is the last video for section 6.2. Stay tuned for section 6.3. We're marching along. We're almost done with chapter 6, and we got a little bit to do in chapter 7. So we'll see you next time.